Dani.
¿Vamos a empezar? Sí. Hola a todos, bienvenidos a esta conferencia. A nombre de la universidad le damos la bienvenida. Es un poco, Min nos va a hacer una presentación. Se entiende que va a ser en inglés, así que espero que no sea mayor problema para todos ustedes. Va a ser la presentación sobre lo que se ha denominado el BIM HD, que es cómo un mayor nivel de detalle en la modelación puede permitir efectivamente integrar el proceso constructivo para la logística de materiales. Vamos a hacer primero una presentación que durará 30-40 minutos y después de eso vamos a pasar por una ronda de preguntas. ¿Correcto? Now Min can start the presentation. Thank you very much for your time.
Thank you for coming here. I am Min Song, PhD student at Stanford. And yes, before starting my academic career, I worked at 5 years on high-rise building projects, 2 years for an owner's company and 3 years for a general contractor, and also on oil and gas projects. So in total, I had around 8 years of experience before starting at Stanford. And I guess after going through many projects in the industry, one of the things that I noticed is that it's not hard to find a good master schedule in a construction project. And also interim schedule, like 6 months look at schedule, 3 months look at schedule. You can pretty much find that at a construction site. And in some cases, even like weekly schedule is being done. But one thing is that it's really hard to find a daily schedule or daily planning being done. I'm sure you can think about a lot of reasons. Maybe for one, it's not a factory. You know, if you go like an automotive factory, it's a consistent production line. And when you go to a car factory, you may have a daily schedule, daily Kanban being produced. But construction, it's got more variables. So producing a daily plan or daily work order is difficult. On the other hand, this is the car factory. And like I said, if you go to a car factory, there is a card where you can order materials from stages in the downstream to upstream. And you can pull the right amount of materials and right amount of resources from one location to other. And based on this information, you can do lots of simulation too. But the general level of detail in construction is pretty rough. It's not as detailed as what you see in the automotive industry. But as a researcher, being at a school, we cannot just say that, okay, that's how construction is. Construction is difficult, we're going to give up. We at least have to try to push the boundaries a little bit, and that's the role of researchers. So that's the topic of my PhD degree, the daily work order and daily planning in construction. And although it's very hard to find a project that has a good daily planning done in construction industry, there are some very few companies that try to do this. And what you're seeing is the daily planning system designed by a German lean construction consulting company called Dries & Sommer. And what they do is they provide consulting service, and this is a typical layout they would have in a construction trailer. So what you see is at one side of the wall, there is overall process analysis. So I don't know if you're familiar with the last planner system. In Germany, they don't call it last planner system, but they have a similar ideas. So this, if you know the last planner system, would be like a phase planning or backward scheduling. And on the other hand, you have the process planning being done. This would be like a 6 weeks look at schedule. And what this consulting company, German consulting company, has a daily, a very detailed planning being done at one corner. And if you zoom in, this is the daily planning board. You might have seen similar boards, but a little bit, it's probably on a little bit rough level. So what they have is that on the rows, they have object tags like room number 1, room number 2, room number 3, or it could be foundation number. So you have object tags in the rows, and for the columns, they have the days. So you have Monday, Tuesday, Wednesday, and so on. So you have 4 weeks going on here. And at the center of the board, you have series of pockets where you can actually insert these daily work orders. And this whole system was very intuitive. Some of the planning system is difficult to teach foremen, difficult to get the idea how it works, but it's color-coded by trade. The carpenter is blue, and the concrete trade would be green. And it's just getting together at the construction trailer and writing down what you're going to do for a week and putting that into the pocket. And if it's Monday, and if the Monday column is this, you come into the construction trailer and take out the cars that belongs to you. That's sort of like your homework for the day. And you go out to the site, do the work, come back to the site, construction trailer, and if the work is done, they flip the card around and they'll put it back in. If it's not done, they will push it to the next day or day after that. So this whole system was very intuitive, easy to train construction people. But one caveat is, in this construction trailer, this is absolutely manual. So everything's handwritten, and there's no connection between a computer and any information on this daily work order. So this is absolutely 100% manual, and because of that, there are lots of information that's missing and only relies on what's in foreman's head. So perhaps the most information that they're missing is the scope information, the scope of this daily work order. And in other words, daily, if you quantify your scope of work, it will be your daily bill of materials, the bill of materials associated with this daily work order. So what I did for my PhD research first is that, okay, this German Dresden Sommer company has a good daily planning system. So I started collecting lots of daily work orders from the construction sites that this DS company was working on. So went to 5 construction sites, 1 in Middle East and 4 in Germany, and started collecting a lot of cars and collected around 831 daily work orders from those sites. And did a study on those cars, and one thing that I found is that, okay, if you are to create a system that rapidly generates daily work order or daily, more precise daily bill of materials, can you actually do that for these cars? And it turns out you can probably do that for 244 cars of 831 cars. That's roughly like 30%. And it further study into those cars showed that those cars were typically related to engineered to order types of materials. In a more a friendly term, it would be prefabricated materials. So when you have prefabricated materials, they tend to have prefabrication shop. And at the prefabrication shop, because they need to fabricate a production unit, they have a very good information on the bill of material for a certain product unit. For instance, ductwork or a spool pipe that is prefabricated shop and brought to the site. It's got a bill of materials and shop drawings for each individual unique duct and spool. So by connecting that bill of materials information in the shop drawing, you can generate a system that rapidly produces daily bill of materials for those cars. So that's about 30% of the cars. But however, like 587 cars out of 831 cars, that's difficult. And further study into those cars kind of showed that those cars were typically related to made-to-stock types of materials. In a layman's term, it would be non-prefabricated types of materials. So for instance, like tracking studs for drywall, gypsum board for drywall. What you typically find in a construction site is that you have a typical shop drawing for a drywall section or a typical shop drawing for acoustical ceiling. Those are types of materials that are non-prefabricated. So if you're to generate daily bill of materials for this type of material, it's doable, but it takes time. You just have to do the additional takeoff based on the typical shop drawing. Sometimes it takes 2 hours or more. sometimes it takes 16 minutes. But you cannot ask a foreman to spend that much time to produce daily information. So, and another interesting study that we did with the 831 cars is that, so 5 construction sites, some of them had BIM, but all of them had LOD 300 or less. All of you familiar with level of development 300 and 400? So LOD 300 is comparable to design documents that you typically come up with at the end of the design process. But LOD 400 is a shop drawing level of BIM. So in LOD 400 BIM, you define very detailed fabrication parts, like bolts and nuts. It goes down to very detailed, and it's typically produced by a contractor who's going to do the actual work. So we used to do the 2D shop drawings, and 2D shop drawings are generally produced by contractors and submitted to general contractor. But the industry is changing toward 3D-based drawings and modeling. So we see that a lot of contractors are starting to use BIM LOD 400 in the Bay Area, San Francisco area. So the industry soon will be changed to use a lot of LOD 400. So that's the distinction between LOD 300 and 400. And studying these cars, if you have LOD 300, you can connect, if you have a daily work order and LOD 300, trying to find the corresponding object for this daily work order. When you have 831 cars, you can only find around 29% of the cars for their corresponding object in BIM if you have LOD 300. But if you have LOD 400, 90% of the 831 cars would have corresponding object in the BIM. So what that kind of meant for us was that maybe if you're going to create a system that rapidly produces daily bill of materials, maybe we should use LOD 400. It should be the sources of information for creating such a system. So what we did was we first built our first version of the prototypes based on the intuition that LOD 400 actually helps. So we imported the LOD 400 elements into the prototype, and you can see that each screen is representing a trade. So the left one is a ductwork, and the center one is electrical boxes, and the right one is track and studs. So instead of the manual board that you saw at the beginning of the presentation, you would have some kind of this board, digital board, at the construction site, and each interface would be dedicated for a certain trade. And it would, like I said, would have the LOD 400 elements in the interface. And you can use that interface to drop the objects that you want and convert that into daily bill of materials. And you will have the quantities, the scope information for that daily work order. But what we found was the problem issue with the prototype version 1 was that if you have a LOD 400, you have so many objects in the interface, and it just doesn't make sense to select individual object. To overcome that, we try to create some kind of free boundary of volume that a user can use and adjust. But that quickly turned out to be not a good idea, because since you have so many objects, connection parts, the user constantly had to check whether the boundary is drawn correctly or not. So there had to be a better method for selecting a set of objects or scope information for the user. And what kind of gave us intuition is that some of these theories in the academia are saying that creating a small batch size actually helps you to reduce risk in construction and also reduce construction duration. A series like in factory physics, which is based on Little's law, and O'Brien's study and Morquist's study at Stanford, they tend to talk about the benefits of creating a small batch size in construction projects. So just a metaphor. So what I mean by creating a small batch size is better. Let's say you have a mouse, and this mouse happens to prefer goat cheese over Swiss cheese. And let's say this black cheese is goat cheese and the white one is Swiss cheese. And if you open up the door for the mouse, what the mouse will do is the mouse will definitely go for the goat cheese first and then eat the Swiss cheese later on. But if you give the mouse some kind of constraint, create some kind of block and say that you can only have the next block when you finish this first block first, then there is no choice for the mouse but to finish first block and second go to the second block and go to the third block. So the benefit of that type of constraint is obvious. This is the first scenario that you saw, and this is the second scenario that you saw. In the first scenario, you're opening the whole floor or whole area for the mouse, so the mouse will be running around the whole area. So that's the space that the mouse needs. But if you constrain the block, the handoff of the workspace can happen at 3 locations. And if you have that 3 location of handoff, the benefit is obvious. You will have a shorter construction duration at the end. Because in this case, the entire area is handed off when the mouse eats both goat cheese and Swiss cheese without a constraint. And in this case, you are creating a block. So the mathematical model of this is a working process equals flow time times throughput. But some people do simulation to show the benefit of creating a small batch size, but you don't need that kind of simulation with the example that I gave you. So if you take that example into the construction industry, what it means is that, let's say you have a painting crew, then if you compare, the painting crew has 3 choices. One is that painting crew work in the unit of an entire floor, or the painting crew can work in the unit of an apartment, or the painting crew can work in the unit of rooms. And if you come up with a schedule, taking out other variable factors, if you just have those factors in the schedule, then if you compare those 3, working in the units of room is the best scenario with the shortest construction duration. So what we did based on that intuition on the previous series, we went to a residential project, a Killen project in Arizona in the US, and started looking at different tasks and trying to find what is the smallest batch size for different trades. So for instance, smallest batch size for track and studs or gypsum board would be a wall. The framers at least need to take a wall as their working space. Although they don't have to take 2 walls or 2 panels, wall or panel is the smallest batch size for a framer. For a painting crew, generally a painting crew, when they're working, they have to occupy the entire room. So the smallest batch size for a painting crew is a room, unless you have like a big assembly room like that. So try to identify for different trades what the smallest batch size would be. Went through 47 tasks, and what we did next was we built the concept of the smallest workspace boundary. So the definition of smallest workspace boundary is a boundary that encapsulates a set of 3D elements, in this case mostly LOD 400 elements, in the smallest workable unit for a certain trade. So for instance, like I said, for track and stud and gypsum board, smallest workspace boundary would be a wall or a panel. If you have a piping, the smallest workable unit is the straight portion of the pipe and the connection, the elbow and T at 2 ends of the pipe. So that's the smallest workspace boundary for piping. And with that idea, what we did is that we brought this smallest workspace boundary idea into this. And so what you're seeing here is not real products, but these are the boundaries for electrical boxes. So electrical boxes in a residential project, they tend to be installed in the units of wall. So each wall is a boundary for selecting a set of electrical boxes. So what it happens is that if you select an electrical box, which is a single or multiple object, it will recognize the workspace boundary, it's encapsulated in, and select all the electrical boxes within that smallest workspace boundary. And then just with one gesture, you can select them and drop them into Dropbox and convert them into daily bill of material.